and some of the advice and comments that he's gotten from the cancer community. I think you would be very surprised. Okay, now we're going to move on to the interview portion of the program, and our wonderful guest tonight, a guest who appeared earlier this year, but unfortunately only by text chat. That is Geordie Rose of D-Wave Systems. Welcome to the program, Geordie.
Hi, thanks for having me.
Yeah, so wonderful to have you here tonight, and I just want to start off with a little review of the last program that you appeared on. We talked a little bit about, of course, quantum computing. There was a big buzz with D-Wave Systems and your potential entry. The first quantum computing company, or first company to commercialize quantum computing, and we'll do a little review of that in the next couple of minutes. But first, for the people who weren't able to attend that text chat, I would like to just for you to introduce yourselves and give a little background on how you ended up getting involved in not only quantum computing, but other areas of, let's say, transhumanist ideas.
Okay, I started off my adult life as an engineer after doing an engineering physics degree at McMaster in Hamilton. And my area of specialization was in semiconductor devices, things like transistors and whatnot.
Sure, okay.
And I felt not satisfied with the level of understanding that I had on how these things were actually functioning. So I went back to school and I did a degree in theoretical physics at UBC in solid state physics.
Okay.
And my research was about what happens when materials get really cold, where the structures that you care about are very small. And that's a very interesting regime where quantum mechanics becomes explicit. And when you look at these systems, the quantum effects become relatively easy to see and detect. So the research that I and my group did was about understanding how it is that the classical world emerges from the underlying laws of quantum mechanics that all matter and energy are presumed to obey. Okay. So during my research at school, I met a bunch of folks who were interested in quantum computing specifically, so that's harnessing the laws of quantum mechanics for computation. And we put together a company with a little bit of founding money, and the company began operations in 1999, and almost 10 years later, here we are, the largest effort in the world now attempting to build one of these machines.
Yeah, and it's very exciting. That was one of the reasons I wanted to get you on the program here, because we talked at the Immortality Institute about many, the future science and progress and how this may affect the human society as a whole. And one of the things that I think is being ignored a little bit by many of the futurist community is quantum computing. Everyone focuses on robotics, nanotechnology, AI, and the bioengineering side of things. And I wonder if not too many people are talking about quantum mechanics because either they don't understand it or they don't think it's possible within the next couple of decades. And I wanted to get your take on that. In the quantum community, is it just that not enough people are knowledgeable about it, that they really aren't talking about it, or is it that they don't think it's possible right now?
Well, quantum mechanics has been around for 15 billion years.
Yeah, it's been a long time, at least 100 years, right?
And our human understanding of it has been around for at least 100 years.
Okay.
But the application or being able to build technologies that exploit the kinds of effects that we're trying to exploit is relatively recent. And the reason for it is fairly clear. It's that the effects themselves only show up under rather peculiar, non-standard circumstances. And in order to build machines that exploit those effects, you have to have very fine control over nature. Yeah. And that's only recently become available, and it's still not widely available. It's not the sort of thing that you can do in your garage. But the the big thing about quantum computing, which is just one way that you can use quantum mechanics for technology, the thing about it that I think is a little bit strange for people is that there's a when you learn about computers, you're taught rightly that all computing models are equivalent in a certain sense. And so if you were to build a computer one way or another way, you don't expect that one would be fundamentally better than the other.
Right.
That whole educational meme is based on
Isn't that
some
based on
which is
Turing's universal computing machine or his theory?
yeah, well,
All right.
that's one universal model. But the thing with all of these models is that they assume that the matter out of which the computer is built operates using the classical laws of physics, and we're at a point now where we can remove that axiom. We can build computers out of things that are not classical, and when we operate them, we see them behaving in an entirely different way, which is quite the ideas are quite subtle, but they're quite awesome.
Sure.
Some folks have characterized them as being able to do the same kinds of get the same end result with less work, like a lot less work, in some way that we don't fully understand how it's happening. There are people who speculate, but yeah, I think that it's a very hard thing to get your head around. And also, I think that in any technology where people don't have direct experience with it, it's very hard to compare it to what they do. So prior to the advent of the laser, it would have been very difficult for people to understand what a laser was. But once you've got one in your hand, you kind of stop worrying about how it works, and you start worrying about more what to use it for.
Yeah, I've got a couple of pictures that I'm going to show for the audience here of your quantum computing chip that you demoed last year, and when you went before the Computer History Museum in your famous demonstration. I just want to again just have you explain now about your particular computer is something called it does adiabatic quantum computation. Is that correct?
Yes, that's right.
And that's different than what, say, most of the popular media has reported on in the past about quantum computers. Correct?
Well, I would characterize it more that the dominant model that's studied in the expert community is this gate model or circuit model.
The gate model, right?
Yeah. So the gate model or circuit model was favored early on because it's very similar to the way that conventional computers operate, in the sense that you have a memory register and you act on it with a sequence of gates, logical gates, except everything is quantum mechanical. Now, that model has a lot of fundamental problems with enablement. So when people try to build something that enables that model, they run into problems that no one has been able to solve.
Engineering problems, right?
Well, there are a host of things. The model asks an enormous amount from the devices that are the subsystems of the computer. So the qubits, the fundamental things that store information, have to be extremely good to be able to run those types of procedures. Whereas some of the other computational models, which are the same in terms of computational power, relax a lot of those constraints and make it easier to run things with what we call noisy qubits.
Okay.
Which are devices that are not perfect quantum mechanical devices, but they are close to it.
Close enough.
So if you allow, close enough.
Yeah. Okay, so that brings me to, I mentioned your demonstration last year, and during our last chat, for our Sunday evening chat, which is now the Sunday evening update program here, we did discuss your future with D-Wave Systems and the future of the quantum computer and how it was going to progress this year. And we did talk about by the second quarter of 2008 having a 512-bit qubit computer ready to go. And I hadn't seen any press releases recently. Where are we at?
So we've decided that the where we're at now is best served in terms of releasing the information on what we're working on in two ways. One is via peer-reviewed science, So we've been publishing an